My name is Marcus Mitchell, fourth year aerospace engineering student at Georgia Tech in Atlanta, Georgia. In this video, we'll be discussing the dynamics of a double pendulum. The double pendulum, composed of two rods of equal length, connected by a hinge that allows for two-dimensional rotation in the plane of the rods. The system is connected to the ceiling by a short string that allows freedom of movement in 3 dimensions for the upper rod. A small mass is attached rigidly to the end of the lower rod. Now, what this does is slightly alter the calculations for the dynamics, primarily of the lower rod, as we treat both the mass attached at the end as a point mass and combine it with the lower rod to form one object. This moves the center of the mass down the rod as opposed to being in the geometric center. In this experiment, we track the motion of the pendulum and compare it to the derived equations. We have 3 unique initial conditions, the first of which we see here. We'll define the parameters for the experiment as such. The origin is fixed at the top of the top arm of the pendulum, just below where it's connected to the ceiling. Angle 1 is between the vertical and the center of the mass of the first arm, located in the geometric center of the arm. Angle 2 is between the vertical of the hinge, which is parallel to the y-axis that's fixed in the first rod, and the center of mass of the second arm, located on the vertical line of symmetry. The respective derivatives are from these given assumptions. Attached are the predictions for the motion of the pendulum with respect to time. These predict a fairly linear motion of both the hinge and the mass at the end. Predictions show that they both start out with high angular velocities that eventually taper off, with the angular velocity of the second obviously being greater than that of the first. Let's see what happens in practice. 2, 3. I gotta do it for a couple more seconds. As we just witnessed, the motion of the double pendulum is characterized to that similar of a single pendulum, with a few more hiccups in between swings. However, the average motion relative to the angles measured from the vertical are quite similar. With this next trial, we will try with the hinge horizontal to the ceiling and the weight hanging directly below. Predictions indicate that the pendulum will act more chaotically than the first, especially as it concerns angle 2. The graphs indicate little to no trend in how the angle approaches equilibrium, until the entire system dies down, in which case it begins to function as a normal pendulum again. Angle 1 also begins slightly chaotically, however, quickly begins to function as it did in the first trial. Let's take a look. One, two, three. Our predictions were mostly correct. However, we should note that the second arm was quite chaotic until the first arm was able to behave like a single pendulum and calm down the system in a way. It is only right that our predictions for the third trial, with a greater starting angular acceleration due to both angles being 90 degrees from the vertical, that the motion of this system will be a little more chaotic than either of the first 2 trials. Both angles seem to show that they will take significantly longer to die down, and the angle velocity seems to be more dynamic than before. However, it's important to note that the graphs for the angular velocity for both angles seem to function similarly, approaching equilibrium at proportional rates. Two, three. We see here that our predictions were a little off and that the pendulum was actually quite calm. It behaved very similarly to a single model, most likely because both the angles and the angular velocities of both arms began with the same initial starting conditions, causing them to accelerate at similar rates. There are many possible causes of differences between the predictions and the final results. There are discrepancies between the assumptions used for programming and for calculations and the realities of the pendulum, such as the fact that the real system does not behave as a perfect pendulum, the forces acknowledged in calculation do not include air resistance, and the imperfections in building the simple machine were not accounted for. However, through our experiments, we have seen how a double pendulum functions both in reality and in digital simulation. Thank you.